Right, so today we're going to look at bonding. And the first one that's probably worth getting into your mind is a sequence of strength. So what bonds are really strong, which ones are really weak. And I've sort of done this here. I've ignored metallic bonds for now because we're looking at things that are made up of more than one type of atom generally. So it's easier to compare things that are made up of different atoms. But basically your strength goes, you've got ionic bonds are very strong because they're an electric attraction between a positive and a negative charge. That's very strong. Then you go to covalent where electrons are shared, so therefore that creates quite a strong attraction between two atoms that are sharing electrons. And these things here create different things. Covalent bonds create covalent networks, and they're also the intramolecular bonds, the bonds between atoms within molecules. So between the oxygen and hydrogen atoms of water, between the carbon and hydrogen atoms of hexane or cyclohexane, and between the carbon and carbon atoms of those as well. So they're quite strong. They take a lot of energy to break. Once you've got past those ideas though, you get to these slightly weaker ones, and again they sort of can be scaffolded from strongest to weakest. So what we're going to focus on are molecules, and molecules can be polar or non-polar. And if they're polar, that means that they have a permanent dipole, which means they have a delta negative and a delta positive side. So for example, something like hydrogen chloride, which when dissolved in water we call hydrochloric acid, has got a big enough electronegativity difference that this bond is polar. Because there's only two atoms in it, that creates a permanent dipole. So the chlorine has got the higher electronegativity at 3.0, so it will have a stronger pull for the bonding electrons, making this side of the molecule delta negative. I draw it as a bit of an S that curls around because I think of it as slightly negative. But molecules have no charge, so therefore the hydrogen side must be delta positive, or slightly positive. If this comes near another hydrogen chloride molecule, then the slightly positive side will be attracted to the slightly negative side. So again, if we have this, the H is going to be delta positive. So there will be a slight attraction between the chlorine side and the hydrogen side of neighbouring molecules. This is why hydrogen chloride has a higher melting and boiling point than, say, for example, hydrogen bromide, because the bond in hydrogen bromide isn't quite so polar. So it doesn't make quite so strong a dipole in each molecule. So the attractions become a little bit weaker. So this is what we call a permanent dipole interaction. And this is basically why polar solvents dissolve polar solutes and things like that, and why polar things have higher melting and boiling points. But then you get things like water, which is such a tiny molecule, yet is liquid at room temperature. It shouldn't be. Permanent dipole forces are not enough to explain this. So there must be another type of bond present which does it. We actually find out what that is by freezing water, and it expands rather than condensing. Normally when you freeze something, you're reducing the kinetic energy, the particles get closer together. Water does the opposite. It gets bigger, which means there must be another type of bond between the water molecules that has a certain size that is actually bigger than how close the molecules can get when they're fluid, when they're liquid. And this is called a hydrogen bond, and I'm going to explain what they are shortly. And they're actually a lot stronger than the permanent dipole forces. The last of these is our temporary dipole forces, and that's why something like wax is a solid. Even though wax is non-polar, at any instant there could be a dipole or more than one dipole within the molecule, within a wax molecule. So therefore it can induce a dipole in the neighbouring molecule, creating temporary dipole forces. Basically, the bigger the electron cloud, the more temporary dipole forces you can get. And the best thing to look at for that is looking at molar mass. So if something's got a large molar mass, it's got a larger number of electrons, so a larger electron cloud. So the chance of having temporary dipole forces is bigger. And so that's why you find that big molecules, like we did in organic chemistry, the big molecules have the higher melting and boiling points, because they have a bigger molecular mass, so they have a bigger electron cloud, so they have more temporary dipole forces. and that's why they have higher melting and boiling points. Going full circle. Right. So what we're going to focus on are just these three. Okay, this is assumed knowledge from last year along with metallic bonds. You still need to know that. But it's assumed knowledge. We're not going to go over that in any depth this year. Alright? So let's start going through those three in a bit of depth. Okay, so on the far left we've got some water molecules that are neighbouring. And the electronegativity difference between hydrogen and oxygen is really, really big. The electronegativity of oxygen is 3.5 and for hydrogen is 2.1. That is a very, very large electronegativity difference. It's not so big that it's going to be an ionic bond, but a difference of 1.4 means that actually the dipole is very much in the favour of the oxygen. So it's more than just being delta negative up here. This bond is actually, the electrons in this bond are spending a lot of time orbiting oxygen rather than orbiting hydrogen. So what that means is if a hydrogen comes near a lone pair of electrons from a neighbouring water molecule, then it can create a very special bond called a hydrogen bond. Now, in the exams, we normally show that by a few dashed lines between the lone pair of electrons of a neighbouring molecule and the hydrogen of this one. And this shows a hydrogen bond. These are really strong. They're not as strong as a covalent bond. They are nowhere near as strong as an ionic bond. But they are a lot stronger than a permanent dipole force. Yes, there are permanent dipole attractions here as well. The delta negative and the delta positive will also create an attraction. That also happens. But this is a very special bond called a hydrogen bond. It only occurs if you've got a very large electronegativity difference. So basically with things bound to nitrogen, oxygen, and fluorine. Just those three. Okay? Nitrogen, oxygen, and fluorine. So when you have hydrogen bound to them. And the reason that it works for these ones is because they also have lone pairs of electrons to allow that hydrogen bond to form. If there were no lone pairs of electrons on oxygen, that bond would not form. Hydrogen fluoride's a little exception to the rule here. You might have remembered last year we said that about 1.7 was the cutoff where we go from an ionic bond to a covalent bond. And the difference here is actually 1.9. But actually if you look at all the properties of HF, it is a molecule. So therefore this must be a covalent bond. With it being such a big value, we know that this has got hydrogen bonds. So therefore we know we could show this bonding to a neighbouring HF molecule like this. I put them a little too close together, but it's okay. Okay, so I can show that large electronegativity difference, lone pair of electrons. Okay, and that thing with the large electronegativity difference includes hydrogen in its bond. All right. Those are your big three. Okay. Now if I compare that to HCl, which is pretty similar to HF, but has a difference of 0.9, this one can't make hydrogen bonds. The difference isn't big enough. Chlorine's electronegativity is not quite high enough. So this will only have permanent dipole forces between the molecules, like I showed right at the start. Right? So just keep that in mind, that fluorine makes hydrogen bonds and HCl doesn't. They have incredibly different boiling and melting points. And in fact, this one, HF, has got a higher one than HCl, but it shouldn't, because HCl has got a much larger molar mass. So you'd expect this one to have a much higher melting or boiling point, but it doesn't. Another thing to sort of show your permanent dipole forces is here, CH2Cl2, so dichloromethane. And I've put the electronegativities for each atom there, and we can see that these bonds here, with only a difference of 0.4, are going to be non-polar. There's no pull either way really here. But 3.0 to 2.5, that's that magical number of 0.5. Doesn't seem a big difference, but it is. It's enough to make the electrons spend a little bit more time around the chlorines. So therefore, creating a dipole there. So because they're pulling this way, this side of the molecule is going to be delta negative, And of course molecules have no charge, so it means that this side is delta positive. So this would make permanent dipole forces with neighbouring CH2, Cl2 molecules. Alright. That one we did last year. You also should have done this one here last year where we look at temporary dipoles. Now the reason I've shown the halogens here is that fluorine is a gas, which suggests that it has very weak forces between the particles. Chlorine is a gas, and also must therefore have very weak forces between the particles. Bromine is a liquid at room temperature, so the forces must be a little bit stronger. And iodine is a solid, but it's a solid which sublimes. So the fact that it sublimes tells us that we can overcome those forces quite easily. Even though there's enough forces there to make it a solid, then they're quite easy to overcome. So why do they form? Well, with a larger electron cloud, the probability of the electrons being distributed absolutely evenly drops to nearly zero. With a smaller electron cloud, though, the chance of the electrons being distributed evenly is almost certainly going to be the same. You're going to have the electrons distributed evenly in a smaller electron cloud, but in a large one you're not. Okay, it's just too many electrons to be pretty sure they'll be evenly distributed. So therefore, at any instant, there could be an instantaneous dipole. So one of the electrons in this cloud is a little bit closer to this nucleus than it is to this nucleus. And so at that instant, that moment, there is a dipole created within this molecule. As the iodine molecules are so big, if it goes anywhere near another iodine molecule, it will induce a dipole in a neighbouring one, creating a temporary dipole force with another iodine. They're easily broken. They're also relatively fluid, so they can break, reform. So this is why iodine is so easy to sublime. Even though it's got lots and lots and lots of temporary dipole forces between the molecules, as soon as you start breaking one or two of them, you'll end up breaking all of them. And they don't just weaken like you have in a polar substance, they break. So they go from being solid to gas. All right? So those are your three main types. Hydrogen bonds, which are really strong, and they're between the lone pair of electrons of an oxygen, fluorine, or nitrogen atom, and a neighbouring hydrogen, which is bound to one of those atoms as well. You've got permanent dipole forces, which are an example of Van der Waals or London forces, which you might have learnt last year. And so this year you call them permanent dipole forces. They are when you've got a molecule which has got an asymmetry of charge, so it has a delta negative and delta positive side always. And you have temporary dipole forces, which are due to the electrons not being distributed evenly in an electron cloud, even though that substance is nonpolar. These happen more readily if you have a very large electron cloud, which is why bigger molecules are solids or liquids, smaller molecules are gases. And it's that link that you have to be able to justify using Lewis structures and 3D diagrams and electronegativity differences.